Are you okay? We'll start now. What is left in course is the generative model, right? In that we are discuss about two major type. One is combinational model. The another one is the sequential model. Example for this combinational model is GMM, Gaussian mixture model, and for the sequential model, example is HMM, hidden Markov model. So we'll start. See, you have the outcome, right? See, for instance, your outcome in the form of a vector, right? So you have the outcome, what you are observing. So this is the vector actually, what you are observing, right? So based on some experiment, it is not just a single element available in that vector. You have more than one element. So we say that it is a vector, right? So there are the outcomes. There are all the outcomes, right? For instance, you can even think of signal, right, like this, and divide that speed signal into the segment, right, that first segment for some time duration, then we have a second segment, and then we have third segment, and so on. So these are all what we call it as the outcome. Segments or the vector basically, right? So you have number of samples in it, right? So that forms actually the vector, right? So this is the outcomes, right? So now what we are assuming in this generating model, so they are assumed as the outcome of one random vector, right? For example, the random vector x probability density function. That's it. That is what the generating model is, right? So these outcomes are assumed as the outcome of one random variable. Let us say in this case it is a random vector, so it is outcome of the random vector x that follows some PDF. Call it as a generative model, right? Once, right, this PDF is modeled properly, we can actually make use of it for the classification. We'll see how that can be done, right? But our goal is to find out what is this PDF, what is right? So we are going to model them, the outcomes of the random vector, right? What is given is what you observe, right? So this is what is given to you. Our requirement is to find out the PDF, the probability density function, right? Because we are assuming that these vectors are actually the outcome of the random vector x that follows some PDF. So we are interested in knowing what is it. Okay, fine. That is fine. But what is that combinational model and sequential model? For example, if you feel that this x1, x2, x3 and all, whatever is that outcome coming, they are not dependent, they are independent. If we feel like this, I mean, if the nature of the experiment demand that they are all the independent outcomes, right, then actually we have to go for what is called this combinational model. I'll tell you what is a combinational model little later, I mean, in elaborate, right? But in case of sequential model, what we assume is they are dependent as a timeline. I mean, what I am telling in this one is x2 depends upon what is there in the x1, right? And then if I see x3, right, it depends upon what is that x2 here. So they have a sequence in it. They have a dependent. For example, the same example what we use here in that. So this is that speech signal we are having, right? So when we spell some sound, some word, right? So suppose that if I sound like stop, the moment when I spell this ST is a sound, right? So there are only some combinations of a sound has to come forward. For example, stop or start, right? Is like that. So it actually depends upon what was actually there in the earlier, right? So in this case, they are what we call it as the sequential, right? So in this case, so if I divide them as a segment, right, like this is x1 here and this is x2 here. So the segment x2, what is coming out of this P signal, this example, what I had taken as a P signal, right? This x2 coming out of this generating model depends upon what is the outcome in the first instant. That is, it all depends upon what is at x1. They are interrelated. That sequence are, right? They are interrelated, right? So if I make use of this property, right? So in modeling generating, right, probabilistic generating model. So in that case, we say that that model is what we call it as sequential model. So that is a major difference, right? So your hidden Markov model is one such example of sequential model, right? So, right, discuss what is that sequential model. Today we'll discuss about this hidden Markov model in detail, right? So what is that about? We'll see that. As I told you, it is basically you are going to have the sequence, right? Say, for example, these are all the outcomes. And this is in particular order, right? So for a particular word, we can say the speech signal. I am considering the same example now, speech signal. So the speech signal for a particular word, which is actually divided into segment like this for a few milliseconds. These are all the segment with few milliseconds. They are arranged in the order, right? Like this, right? So now this forms a sequence, right? So how it is getting generated? What is that PDF or the probability? What is that probability you are going to assign to it, right? So we are going to assume in this case, right, all these three, x1, x2, x3, and so on up to this xn, they are going to generate, right, from three states. So in this case, this k equal to 1, k equal to 2, and then k equal to 3. They are all the state here, right? For example, let us say that x1 is getting generated from the state 1, right? This is state 1 now. This is state 2. And then this is state 3, right? Let us say that the first x1 is getting generated from state 2. Let us say like that. So this is the starting point now. It is the vector x1 is getting generated from the state 1, right? So here x1 here, right? Then see what is it by generating? Generating means, as I told you earlier, we are actually for the density function, right? Here, all these three states, right? The being in that particular state, of course, I told you that x1 is getting generated from the state 2. Okay, fine, that is fixed. Let us say that x1 is getting generated from the state 2. But what is the probability that x1 is getting generated with the state 2? I mean, what I want to say here is, after being in a state 2, what is the probability that, right, you get x1 alone? I mean, this is basically you get an outcome random vector here, vectors what is available in this, right? So one among this one is going to be your x1 in this. You understood the point, right? So what we have to understand is, first of all, you have to understand that the x1 being generated from one particular state, that is the one thing, right? So let us assume that x2 is getting generated with state 2. Now that is fixed, right? I mean, the first one, the first vector is getting generated with this state 2. And then being in the state 2, there are more choices, right? So for getting that vector getting generated from the state 2, because state 2 doesn't mean that it is going to generate x1 alone. State 2 is capable of generating any vectors, in fact, right? Any vectors of that length, right? But the probability of getting this x1, a particular x1, it follows the density function. Here I have used the Gaussian contour here. This is that 2D, right? 2D Gaussian. I mean, here we assumed that the vector is of size 2 cross 1 for understanding purpose. Each vector is actually having the size of 2 cross 1. And that is the reason we are able to show it in 2D space. And they are all the Gaussian contours. Contours means having the same density function values, right? So what I mean by that is, for example, if I trace this ellipse, the density function associated with this, all are going to be the same. The value is identical. If I see this, if I trace out this like this, if I trace like this, the density function associated with this, this contour is going to be that identical. It is like that, right? So like that. That is what I mean by that contour, right? So now that's what I said. We have a probability for this x1, particular x1, right? So because this being in a state 2, right, there are many vectors possible getting generated from this, right? So we would like to know what is exactly that probability of x1 being in the state 2, right? It actually follows this Gaussian distributed, Gaussian density, right? So it means that state is actually described by the Gaussian density function. Means, let us say this Gaussian density function in higher dimensional space, it means that it is described by its mean vector, right? And let me put it as mu2 and sigma 2, right? Because it is of state 2, I am using that one. So it is Gaussian distributed with mean vector mu1 and covariance matrix. Again a Gaussian with mean vector mu3 and then sigma 3. So here what I am trying to say here is the state, right, described by the density function, which is further, in this particular model, we are assuming that it is Gaussian. So by its mean covariance matrix, the shape, the tilt of this all depends upon the covariance matrix, right? So the mean vector is basically the mean here, the dot is a mean in it, and the tilt, that angle, it is actually basically what determines that. So this density function of state 1, state 2, state 3, all are actually described by sigma 1, mu1, sigma 2, mu2, and then sigma 3, mu3. As I told you, now x1 is getting generated from the state 2. This is the assumption. I'm just saying that, right? So let us assume that x1 is getting generated from the state 2. Then you have a probability of moving to the next state. State 1. Right? So it needs to jump to the next state. I mean, there are three choices actually: being in the same state, right? Or it can go to the next state. I mean, go to this state 3, right? It can actually go to that state 1. It is more general, I'm telling, right? Right? So now currently it is in state 2. Now there is a chance that it can go to state 3 or state 1 or being the same. So there are three choices. And this probability is needed. What is the probability, right? So you have, what is the probability that the state is getting changed to what? For example, 3, you are at what? State 2. So we need this information also. What is the probability of moving to this state 2? And then you are being in state 2, right? In the same state, right? And then what is the probability that you are trying to move to the state 1? You are being in that state 2 again, right? So these probabilities are also needed in this generating model. We need this information also. This is what we call it as this transition probabilities, right? So these are what we call it as this transition probability, right? So let us assume that, so we have three choice, of course, I told you, but let us say that the actual movement, right, it is random only, but I'm saying that the state has been changed from state 2 to state 3, right? Now this x2, the second part, right, the x2 is getting generated from this state 3 now, right? This x2 is getting generated with this state 3, right? And with, of course, the probability is there, right? So what is the probability that exactly this x2 is getting generated from where? The state 2. We have a transition probability, right? The state has to change from state 2 to state 3, and then being in the state 3, right? The probability that x2 is getting generated from that state is actually needed, right? Yeah, it's very interesting question what Sri Vardhan has asked. Is it the same vector? Can the same vector be generated from different states? The answer is yes. It's a very important and interesting question. The answer is yes. That is the important point. Your observation is good. The point is, they are all the Gaussian model. Moment when you are modeling it as a Gaussian, right? Here I have done it in 2D, right? If I plot it is in 1D, you know that the Gaussian density is like this, right? It goes up to infinity, and this side it goes up to what? Minus infinity, right? So if it is a 2D, you can imagine this actually in the form of a bell shape, right? So that is the only difference, right? So it means that the element of the vector, if it is modeled as Gaussian, can have the range all the way from minus infinity to plus infinity, ideally speaking. But the probabilities are going to be very, very less, right? So those things, right? But see, even though the contour I have stopped with 1, 2, 3 contour, right? In fact, we have a contour continuously. It is not like the discrete contours like what you see here. It is more continuous. It is more continuous. We can say that it is fully filled. It is not just like what you are seeing here, right? It is completely filled. It is completely filled now, right? So the contours are actually, and it keep on growing also. It is not going to stop here. It keeps on growing. It keeps on growing. It keeps on growing like this. In fact, it keeps on growing up to infinity. And there are overlapping occur. no doubt in it. So you have, you see, so if I put this contour like this, you get a overlapping, right? So there is a place, you get this overlapping. So this is the place, for example, this is that overlapping, right? So this vector is getting generated from this state as well as this state. As you mentioned, it is a very interesting, important question. This is a vector getting generated from the state 1 as well as state 2. Both are applicable, but the probabilities are different. When it is a state 1, you have a different probability, but when you are in state 2, we have a different probability. But both are capable of generating the same vector. Your question is correct. It's a very important question also, right? Okay, so let me go back to this original track. What you said is right. Okay, so now let me, yeah. So as you said, this is going to have this mean vector mu1 and sigma 1 here, and this is the model with mu2, sigma 2, and this is with what? Mu3 and then sigma 3, right? And as you know, the contours are continuous and it is actually going up to infinity, right? So that is important point, right? The same vector going to get generated from 1 or state 2 or state 3. All it is going to be like that, right? Okay, now as I told you, the first x1 is getting generated with the state 2, and then you have a transition, right? So let me put x1 here. So you have a transition from this to this, and then x2 is getting generated from state 3, right? And then it could be in the same place, or it can go to that x1, here the state 1, right? So we have a transition probability, right? So let us say that x is also going to get generated from the same x3, right? So the transition is happening like this, and x3 is getting generated from this, right? And then let us say it has actually moved to this, and then x4 is getting generated from this. You see that? So the complete sequence, x1, x2, x3, and so on up to this xn, right? They are sequentially generated, and that is the name we call it as a sequential model. That is the name what we give it as a sequential model, which we call it as hidden Markov model. I'll tell you what is that hidden here, and then a Markov model, right? So here, this type of model with states and generation is basically the Markov model. But what is that hidden here? That we'll discuss later, right? So you see what is there in the right hand side. This actually shows the transition. I'm not properly, we cannot trace it out, but you can understand the concept. It starts with this state 2, and then it has gone to that state 3. And if you properly trace, we can understand it's being in the same state. And somewhere from here it is very clear that it is getting moved to the state 1, and then keeps on generating from the state 1 only, and then some place there is a transition from this to probably this may be here, right? So, and because the arrow mark is not there, we are not able to properly trace it out. But this actually we have with what again state 2, there is a transition, and then this vector is getting generated with state 2, and then this vector is getting generated with state 2, again state 2, and then going back to state 1. It is like that, and then coming back to state 3, like that. So this is just the example to illustrate how the vectors are getting generated. This is a typical example of how the sequence of vectors are getting generated from this HMM model. Okay, fine. What is that probability of a typical sequence of vectors getting generated from this model? So now what is this model first of all? The model involves what is now we are able to understand that the model means we are interested in knowing what is this mu1 and sigma 1, and what is that mu2 and sigma 2. and what is my mu3 and then sigma 3. That is the first thing, right? We are interested in knowing that, right? And what else we need? So we introduce a new variable called a subscript ij, right? This is the state transition, right? I is actually takes the value 1, 2, and 3. It means that, so there is a change in that state happening, 1 to 1, 1 to 2, like that, right? So it is like A11, A12, like that, right? So we have this A33, right? Being in the same, being the ith state, right? What is the probability that it is getting moved to what? So, but it is very clear one thing, that if you are at the state 1, there are only 3 choice possible, right? There are only 3 possible things available now. So if I sum up this probability, that forms a partition probability. So if I sum up this probability, right, like A11 plus A12 plus A13, that should necessarily end up with, that forms the partition, right? So that is one property of the transition probability, right? And one more thing is where to start. I mean, we have a transition from 1 to 1, 1 to 2, 1 to 3, and so on, right? Where to start? I said in this particular example, the first vector starts with what? The state 2, but it is not always necessary that needs to start with what? State 2. So we need that probability. So that is phi 1, phi 2, and then the probability that the vector starts with what? The state 1, that is phi 1. What is the probability that the vector starts with state 2, that is pi 2 here, and then pi 3 here, right? Starts with this state 3. And of course, here we have a property pi 1 plus pi 2 plus pi 3, right? So that should end up with 1 again. So this forms the partition set. So this also should end up with, in this case, right? So we have what is called transition probability, and then we have here this so it is like that. Now let us calculate a typical vector. Now vector of generating a particular sequence of vectors, right? Like this, x1, x2, right? It goes like this, and then xn. What is this probability, right? First of all, we would like to know that, we assume that we had a particular sequence, as I told you earlier, right? So let us, to make it a little clear, let us say this n is going to have length of 8, or let us say 5, okay? So let me take it as a 5 and then give you clarity on that. Like x2, and then x3, then x4, and then x5. And we have the information regarding where it starts and where it has actually moved and so on, right? For example, let us say that it starts with the state 2, right? So the probability that the sequence, right, is actually starts with that state 2 is, first of all, we have to write this probability pi 2 here, that event should happen, and then we need to have that vector getting generated with that state 1. So probability of x1 getting generated with the state 1. Let us put that state 1 as S1 here for understanding, right? And then there is a movement of state, right? So we need to move that state transition needs to occur, right? So let us assume, as I told you, let us assume that the transition is like this. So what is the property that the state has moved from S1 to S2? So this is going to be your probability, right? And then being in the state, this is state 3, right? So let me put it as, okay. No, I made a mistake. So this is going to be your S2 because you are at state 2 here, right? And then you are moving from state 2 to state 3. And then X2 is getting generated with state 3. Yes, right? And then there is a transition from state 3 to, let us assume that it is getting generated. I mean, the transition is itself. I mean, the next state is S3 itself. So we have probability of S3 given S3 now being in the same state, right? And then, and your X3 is going to get generated with S3, I mean state 3 now. And let us assume that the state has been changed to S1, right? So we have what is called the state transition, S1 here, and it starts with S3 and it has moved there. And then we have this X4, right? So X4 getting generated with S1 here. And then, and let us assume that it is same state in the next, right? So we have a state transition probability, right? It is S1 to S1, right? From S1, it is actually moved to this S1. And finally, you have this X5 is getting generated with S1. I hope this is very clear to you, right? So let me explain once again. You are at the beginning, you are at the state 2. So this event should happen. This probability is pi 2 here. And then you are in the state 2 and X1 needs to get generated from that. So we have this probability of X1 given S2. And then there is a transition probability, right? So your state is changing from S1 to S3, right? So that is described by this. This is a transition. And then again, you are at S3 now, this X2, that second vector, right? Your second vector needs to get generated now at this point from state 3 because you are at state 3 only. Again, we have this state transition from state 3 to state 3. You are in the same state. So that is happening here. And then being in that state 3, your X3 is getting generated here. So X3 here getting generated from this state 3. And then you have a state transition from S3 to S1. You are at state S3 and then you are moving to this S1. And now you are at state S1 and your X4 is getting generated from state, right? Like this. And then you are actually moving from state 1 to state 1, mean that you are in the same state. So what is happening now here, right? And finally, the vector X5 is getting generated from the state 1 in this, right? So this is what we call it as the generating probability. What we got now, this is the generating probability. Generating probability. Right? Okay, fine. If I want to know about this generating probability, what really we need this transition probabilities and this probabilities pi 1, pi 2, pi 3. This priors also we are in need of to calculate this, right? So they are hidden. They are not available. It is not actually given to you. We need to actually identify those unknown. And that's what the name hidden Markov model. This model is what we call it as Markov model. And these parameters are not known. And these parameters actually you need to estimate, right? And hence the name what is called hidden Markov model. And this parameters actually you have to estimate from the data given to you. What is given to you is the data. Data means you'll be given the speech signal, the segments, right? So that is the data. For example, in this example, let us consider that you are given some group of vectors available, right? So it is not just one vector, right? So 1, 1, 1, 2, 1, 3, then 1n. This is one such sequence. And then we have another sequence x21, x22, right? x23, and so on up to this what? x2n. Another vector, right? So you are given like this. This is the data set given to you. You are actually collecting this vector with sequence m2, right? It goes like that. This is m n with vector here. There are m vectors in this. You can see that this first vector, second vector, and so on. There are m vectors available. You are only given this m vector. That's all. But you have to identify what is my pi 1, what is that pi 2, what is that pi 3, what is that aij, and not only that, we are interested on what is sigma 1, mu 1, sigma 2, mu 2, sigma 3, mu 3. All these unknowns are in need of, right? Again, one more question from Shiva Shankaran. Are the number of states known to us or they should be assumed? The number of states actually is not known again. There are ways to find out initializing the number of state by using what is called k-means clustering, right? So that we will discuss while discussing about GMM, right? So now this lecture assumes that we are fixing up the number of state, right? So number of state is also not known, in fact, right? So that needs to be assumed, right? There must be some way to initialize the number of state, right? So one method is by using this clustering technique. K-means clustering technique is unsupervised clustering technique, right? That comes that we will discuss while discussing about this combinational model, right? So now let us assume in this case the number of states are actually fixed. Okay, so we have 3 states and these are all these unknown, right? So once this unknowns are known to you, right, then your model is ready. Okay, fine. What is the use of this model? Basically, you go this slide. I are going to discuss how you are going to get this parameter thoroughly. So that is what the main objective of this discussion. How to get this? That is one thing we must know about it, right? So okay, let us assume it is known. We have a model now. HMM is ready. HMM is ready means what it really mean by that is your parameters, all the hidden parameters are ready. You got that model, right? Using the training data set, what is available to you, and you got a model ready, right? So what is that you are going to do? The hidden Markov model, right? You are going to form a hidden Markov model for, let us say, the problem of classifying the digits 0, 1, and then let us say 9. And it is a speech signal, right? So these are all the different sounds, right? 0, the word, the speech segment, that 0, that you are going to divide into further, right, subblocks, we can say, and each subblock in that is going to be the vector. What I'm trying to say here is 0, right? 0, 1, 1, 2, x1, and so on up to this x1. You are talking milliseconds. You have to understand that. Seconds like that. and each word occupies at least half a second or 1 second, some cases, right? So imagine that each vector here, this actually occupies 20 millisecond data. So this itself is a vector for you. What I'm trying to say here is, the moment you spell this, right, the word 0, that will actually gives you the sequence of, right, vectors, sequence of vectors like this. Okay, so it is like that. So as previous slide, I mean previous discussion, so the number of vectors, you can assume that it is n vectors, and there are some signal processing method to make the number of segment to be make it as identical, because in practice it is not going to be exactly the same. 0 will not get repeated, right? When I sound 0, right, so the length of the speech signal is going to be different. If someone sounds 0, then the length is going to be different, right? So there are that we are not going to discuss. I'm just telling that we need to do some sort of signal pre-processing. We call it as pre-warping technique and all, in such a way that the length is going to be n. So timing, we are not worrying about it. So what I'm trying to say here in this case is, every digit now it is getting replaced with the sequence of vector like this, with of course the same length like this, So it is like this, length 1, 2, 3, right, n, right? So, right. So now the point is, the 0, the digit 0, when you spell, right? So you are going to collect as a training data. It is not only from the single person. You are going to collect this one from multiple, right? Multiple attempts, and then multiple and different people, right? Multiple, right, subjects. The peoples are going, I mean, we have to collect it from different person, right? And for the same person, we can collect it many times, many attempts, right? So the word 0 itself, is going to have a data set in that. What I'm trying to say in this case is, you are actually going to have a HMM model for the digit 0, HMM model, which is called, let us say, HMM subscript 0. This is a model ready for the digit 1. And you need to have a HMM model for digit 2. I mean 1, for example, like this HMM, and then 9. You are having like this, right? So we have to create this model. That's what we are going to discuss, how we are going to create this model. But after knowing this model, right, so you have this sequence of model like this. So this is going to be your HMM 0, and you are going to have HMM 1. It goes like that, and then you have the digit 9, HMM 9, right? So it's like this, right? So what you are going to do is, you are going to give the input vector under test. This vector, we don't know whether this vector is corresponding to the word 0, right, or 1 or 2 or 9, right? So we don't know that. But this is a vector given to this model. And what is this HMM 0 model, hidden model is going to do is, it is going to actually calculate this generating probability. Just now, I mean, we have discussed about this generating probability, right? So we are going to actually compute this generating probability for the individual model, right? So you are going to have, assuming that this corresponds to the digit 0, we get this probability, right? And if you assume that it is 1, we get a probability with HMM 1, and then and so on up to this HMM 9. We get a probability, right? So it is like this probability, let us say that it is P0, and this is P1, and then you are going to have this P9, right? So now this is given as an input to this decision block. It's a very simple decision, right? So what you have to do is, we have to find out whichever is the maximum. So we have to find out maximum among this P0, P1 and so on up to this P9, right? So suppose that if P3 is maximum, we declare that the digit is 3, right? It is like that. So this is what the way how we use this HMM, right? Sequential model for classification, right? So, okay, to do this task, what really we need is the model. That is the main task. The model is needed, right? So what is given to you? For example, if I want to model HMM0, we need a collection of words spelled by various subjects, and each subject needs to repeat that word many attempts, and those words whatever you have collected, they are all the training set, and using this training set we need to model this HMM. Modeling means, once again I tell you, it means that you are, let us say you are initialized with 3 state, then you are interested in knowing about this covariance matrix mean vector for I equal to 1 to, more general it is a K state, right? And then we need to know about this prior, right? So pi K, we put this I here, right? So again I ranging from 1 to K, and then we have this transition probability Aij, right? So I is again 1 to K, and then J is also ranging from 1 to K, right? So these 3 things are needed, right? State transition, the model of the state, right? So in this case you are using that it is a Gaussian, so mean vector and covariance matrix prior, these things are needed actually. So how to get this is the task. So that is what we are going to discuss in the next class, right? So before that, before we wind up, I just wanted to introduce you one variable called latent variable, and then we'll continue in the next class from that. So what is that latent variable? Each sequence, right? So you have this x1 up to this xn, right? So here we have introduced variable, the latent variable, as the additional. It is not actually the part of the data. We are going to introduce that variable here, z1 associated with what? Generating this x1 and so on up to this zn, which actually describes the state. Means z1 vector can take the value like this 1 0 0, or it can take 0 1 0, or it can take the value 0 0 1. Suppose my z1 is 1 0 0. If it is 1 0 0, it means that the x1 is getting generated with state 1. Suppose that my z1 value is 0 1 0, we can interpret that x1 is getting generated with state 2. And suppose that if z1 takes the value 0 0 1, we can interpret that x1 is getting generated with the state is 3, right? So this variable z1 all the way up to this zn, right? This variable is what we call it as latent variable. We are going to use this latent variable in, right, in solving this problem, because it is not so simple. It is very complicated problem actually, sequential model, right? Hidden Markov model particularly, right? So we are going to introduce this, and we need to formulate that objective function, right? And then we have to solve for the unknown parameters. How we are going to solve that, we will discuss in the next class, right? We will stop here.